Hello, this is Pete Cacciopi, and I'm going to be walking you through combining machine learning and optimization with Gurobi and sklearn. So I'll be discussing the machine learning section, and then I'll pass it over to Daniel for the optimization section of the slides. So machine learning is such a big topic that it's the analogy of the blind man and the elephant probably applies here. So let's just review what parts of the elephant we're going to be laying our hands on and what part of the elephant we'll be leaving alone. So today we'll be using supervised learning. So supervised learning is probably the most common sense part of machine learning, in that we will be studying a historical table in order to make predictions, in order to make inferences and thus make predictions about future data. The key thing we'll be spending most of our time on, we'll be discussing how to select algorithms appropriately and also how to use the right parameters for those algorithms. So the term hyperparametric optimization sometimes gets tossed around. That's a machine learning term that's a bit confusing if you're coming from optimization, and that what they're really talking about with hyperparametric optimization is just parameter tuning. We're also going to be talking about how training and prediction are often separated from each other. So I'll discuss that a bit in the slides, and also at the very end, we'll be giving a deployment example where you can see how the due diligence step of assessment and training is done with less frequency than the prediction step, how you can facilitate that. So unsupervised learning, so just to give a little more terminology, supervised learning is characterized by the presence of a dependent column in the data table, and the dependent column is the data over which you'll be making future predictions. Unsupervised learning lacks the dependent column. It's used more for analysis like clustering or image analysis. So when your data set contains time information, like timestamp information, then there are more advanced techniques that can be used to make even better predictions based on time-based patterns, but that won't be part of today's presentation. And finally, deep learning, I think it bears mentioning because deep learning is that part of machine learning that's probably getting the most press. When you're reading in the newspaper about the latest and greatest breakthrough from Google, like when you're defeating the Go champion, that's a deep learning example. But on the crawl, walk, run spectrum, I think deep learning is more in the track star territory, so we won't be discussing it today. So for the optimization piece, you'll first see an optimization engine put together kind of almost as if it's in the scratch phase. So obviously this is a Jupyter notebook that we're going through, and you'll be able to download the notebook that generated these slides and execute the code yourself. And the part of the demonstration here is how if you were using a notebook for exploratory programming, you could build an optimization engine sort of in a trial and error way. And then once you had it working, you would be able to cut and paste the code with very little change, just add some boilerplate to make a Python script that stands by itself and reads and writes from standalone data. And then that script can also be uploaded to a platform to create an application. The type of problem we'll be studying today is the type that's characterized by the presence of a potential combinatorial explosion. So that's the sort of issue where there's the size of the solution space is growing exponentially. So here we'll be selecting the products, and as the number of products grows, the number of solutions you need to consider is growing exponentially, and thus, even though today's example is so small, you could enumerate all the possible examples. The real-world problem from which this sample problem was derived had a solution space, I think, in the hundreds of billions or something beyond that. I mean, it was obviously way too big to be enumerated. But Gurobi performed perfectly and ran in just a few minutes. And finally, in Daniel's section at the end of this slide, he'll be showing how you can kind of teasing over a little bit into the area of stochastic programming. He'll be showing how the randomization that's inherent in this particular machine learning predictor we'll be using can be used to generate a realistic range of solution inputs that can then be used to validate your solution, to simulate how your solution behaves under a range of real-world conditions. So again, just to emphasize, we'll be using Python throughout here. So Python has really changed. I think it's worth, especially as we're discussing using machine learning and optimization together, I think it's worth pointing out that not everyone might be aware of this, but that Gurobi has really been the thought leader in the optimization space in terms of recognizing the value of Python early on. So I learned Python. I started doing optimization with Python, I think, around 4 years ago. And at the time, the only real way you could learn how to do it was by studying the Gurobi examples. They were the only people that had sort of a proper algebraic API, and they had really far more examples. You know, they had all the documentation online and videos online. So I think we all owe a credit to Gurobi for helping to pave the way in the area of Python. So the problem we're studying today is the soda promotion problem. We have a business planner that's trying to put some sodas, whose goal is to put some of his sodas on sale for the Super Bowl. And the goal is to maximize the overall sale of soda while obeying various business constraints. So inherent in this problem is the ability to predict the expected demand of soda based on the price of soda. So as a result, we need to use machine learning to prepare our inputs for the optimization problem. In order to predict the demand for soda, we'll look at a historical data table. So I think this is the first slide where we're pulling up some code. So again, for time purposes, we're going to be going through the code fairly quickly. So again, here we are uploading using pandas to upload a data table that has the historical data for the sales of soda. So this is a table with 596 rows, 14 columns. So in machine learning terminology, the rows are often called samples. And that kind of makes sense. If you think of what a row means here, it's for some historical week of data. You can see for a given product, how much of it was sold at that price, and you can see information about what that particular week was like, you know, what holidays were included in that week, what the temperature was like, and what the preceding sales were for that week for that type of soda. So again, with the terminology, the rows are samples. The columns are sometimes called variables. I'll try to stick to calling them columns so as not to confuse whether we're talking about machine learning or optimization. The column that you want to predict in the future is called the dependent column, and here that's historical sales, which is an equivalent to expected demand for future predictions. For the other columns, so all the other columns other than the dependent column are the independent columns. In the future, you'll be looking at an independent column submatrix. So that I'll throw that term around a bunch, and that just means a data table that has only the independent columns. The independent columns here have different types of data, as you can see. Some of the data is numerical. For example, the cost, the temperature, the sales. Some of the data is categorical. So even the type of product itself is categorical, and obviously the presence or absence of holidays is categorical. Categorical data needs to be converted to numeric data in order to be used by the machine learning algorithms. Lucky for us, Pandas has a very useful routine just for converting categorical data to numeric data. So this is the get dummies routine. So you just pass it a table, you tell it which columns are categorical, and you give it some guidance as to how to rename the dummy columns that will be created from the categorical columns. And as you can see, what happened was the numerical columns were kept as is, and the categorical columns were all removed and then replaced by these dummy columns that only have Boolean data, only have zeros and ones. And if you think about it, it makes sense. It's always converting to zeros and ones, even if it needs to make more columns, and that's because you don't want to convert to a numerical sequence, because then you'd be indicating that some categories are more similar to each other than other categories, right? Because 2 is closer to 1 than it is to 0. So instead, you always convert to zeros and ones, even if you need more columns. Once you've got a data table that's fully numeric, then you can assess which machine learning algorithm is most appropriate. So we're going to consider 4 machine learning algorithms. This is the sklearn library. So I guess I didn't emphasize this point up till now. All of these libraries, except for the TICDAT library, which I'm going to show at the very end, all of these other libraries are part of the Anaconda distribution that you can get from Gurobi. And the machine learning libraries we're going to be considering are decision tree, random forest, linear regression, which is sometimes called ordinary least squares, and bagging. We're going to, with just a brief nod towards picking the right parameters, we're going to consider random forest twice, once with 100 estimators and once with the default, which I think is 5 estimators. true hyperparametric optimization gets a lot more complicated than this, and that probably would merit its own deep dive. But for our purposes, that'll be the extent of parameter assessment. And the other point is that I'm using a lambda here. Instead of calling the objects just those factory functions just once, I'm actually wrapping them inside an anonymous function. And the reason I'm doing that is to emphasize the point that I'm getting a fresh copy every time. So technically, that's not needed. The sklearn libraries are smart enough that if you call fit twice, then the second fit is really a refit. So it always is blowing away its memory every time you call fit. But I like to emphasize the point for how cross-fold validation works, that I'm always getting a fresh copy that has no memory. So I already teased this topic. Overfitting is the easiest sort of trap to fall into when you're doing assessments. The danger of overfitting is you don't want to assess an algorithm's ability to simply be a mockingbird. So if you train on the entire data set and then predict on the entire data set and then assess that entire data set predictions, then an algorithm might appear to be better than it really is because all it's doing is echoing back the original data. So instead, you want to simulate what would happen in more realistic scenarios where you're expecting the future data to be similar to the historical data, but not to have identical rows with the historical data. And the utility for creating that sort of simulation is the train test split routine. So what this routine does is you pass it the independent column submatrix and the dependent column, and you tell it the ratio of the train test split, and it will split both the independent column submatrix and the dependent column into training sections and testing sections. And here I told it to split with a 1/4 split, so that's why we have 447 for training and 149 for testing. Now, by repeatedly doing this, we can do a more realistic simulation of prediction accuracy. So here I'm performing 4 iterations. For each iteration, I'm doing a train test split. So then I have a training section and a testing section of the independent columns, a training and a testing section of the dependent column. And then for each algorithm, I train on the training section. Both the dependent and the independent are used for training. And then I make predictions based on just the independent testing section, and I keep track of all those predictions. And I also keep track of all the testing section of the dependent column. And when I'm all done, now I'm back to the same number of rows. So I'm back to the 596. So I have 596 actual values and 596 predictions for those values. But none of those predictions involved trying to predict a row that was exactly the same as a row that was trained on. So now we have a set of actual values and we have a set of predictions. So now we can assess the quality of the predictions for each algorithm, and we'll start by doing that graphically. So again, the Anaconda distribution has this nice matplotlib library. So bear with me, I know these graphs might be a little hard to see with this resolution. If you actually are running this notebook yourself and you take out this matplotlib inline piece of code, then the graph will appear in its own screen and you can make it much bigger and examine it more carefully. But here we have the actual values plotted as an identity function. So that's x equal y, purple line. The overestimates are appearing above it and the underestimates are appearing below it. And this just gives you a visual sense of how accurate your algorithms are. You could look at these colored dots and see which algorithms are coming closer to the line, which ones have really far outliers. Each of the different algorithms has a different colored dot. You can do a similar visualization, except here we're computing the relative error. So if you don't have a lot of experience with data frames, this sort of bit of Python looks a little bit magical. It's actually just a testimony to how great Panda's library is. This is a vector, and also this is a vector, and of course this is a vector, but of course this is not a vector, this is just a constant. But all this logic computes correctly, computes in the intuitive way you'd expect, and creates a new vector. So that's Panda sort of is cleverly built. They call that functionality broadcasting, and it's cleverly built to accommodate functions, broadcasting of functions, and broadcasting of operators with constants. And so by computing the relative error, the best possible relative error is 0. And here you can see a nice graph. The algorithms that are closest to 0, I just ordered these numbers sequentially. You can see I've got the numbers that are closest to 0 indicate the best accuracy. And one more graph. This is the box plot. Again, I'm doing the box plot for a given. I'm creating a simple function that for a given algorithm will look up the prediction for that algorithm, and then it will graph the % error again. And this is the box and whisker graph. This graph is drawn by, this is the top quartile, the bottom quartile, and these are just the scattering of the data points that don't fall within that range. And you can draw it for bagging and random forest, which I'm picking those out because those are the two that tend to work the best for this data set. And so visualizations are helpful. You can build a lot of intuition with how the errors look using visualizations, but there's also a more formal way to do things. So if you're looking over that code and we're thinking, boy, that code looks kind of repetitious, is there a simpler way to just get a single number for purposes of performing an assessment? There is. It's the cross-val score routine. And here you can pass it an object that's capable of fitting and predicting. And again, this is exercising sklearn's ability to fully refit whenever you call fit. You pass it the dependent column and the full dependent column, and you pass it the full independent column submatrix. You tell it how many cross-folds to perform, and it will perform basically just the same sort of logic we just saw. We'll do train test splitting, training on the training section, and predicting against the testing section. And then it will give you a measurement of accuracy. By default, the measure of accuracy it gives you is the R2 error. So that's the statistical error where 1 is perfect correlation, and numbers smaller than 1 indicate weaker correlation. And I'm just taking the average for all the different crossfolds and all the different errors. And you can see here that the big random forest, as you might have guessed, is the one that has the highest correlation. So that's random forest with 100 estimators. So now that we know that big random forest is the most accurate, we can train on the entire historical table to create a predictor object. So here fitted is our predictor object. This is that line of code that I think disturbed some people, that it's perhaps a little too clever for my own good, but all I'm doing here is looking up which index big random forest was, then I'm capturing the function that creates that object, and I'm creating the object, and then I'm calling fit on it with the whole historical table. So this object, we call it the predictor object. So this is the point that if you were in a more of a production environment, you would want to store that object somehow, because all of the stuff up till now is sort of a due diligence, and planners usually will want to make predictions more frequently than they would need to do the due diligence of assessment and retraining. Python has all sorts of serialization options, and then you'll have to work with your own platform for how to serialize. You can see one way that it was done at the end of this talk. But let's assume now that we're just diving straight into making our prediction. Now we load another table. This is the table for the Super Bowl itself. As you can see, we don't know the sales for the soda. This is the table that has all that other information, has the independent columns for the Super Bowl, but not sales, because the sales is what we're going to try to predict. And again, I'm calling the get dummies on it because this will have the same categorical columns. And of course, because there's only 36 records here, the previous one was 596, I believe. So it's not surprising that once you've called get dummies, the Super Bowl table that was created from get dummies has fewer columns because the Super Bowl data has less categorical range. That's easy enough to just walk through all the columns that are in the historical dummied up table, and any column that is present there but not present in the Super Bowl dummied up table, we'll just double check that it starts with our dummy prefix, and we'll just create an all zero column indicating that that category is absent. And then now we've got a properly organized table with matching columns. We can call predict on our predictor object and create a vector of predictions. And now prediction in hand, we can perform our optimizations. And I believe Daniel should have control.
Thank you, Pete. Recapping a bit. So what we've been doing up to now is wrestle with the data to have good estimation for what the sales are going to be for the different price levels that the company is considering. So now we have to go back and define what's the logic of the problem that we want to solve. Let me do that by defining the equations that really states the mathematical problem we want to solve. So as we said at the beginning, what we want to maximize the sales. And we need to make a decision. We have to define what kind of price we're going to use for every soda product. And that's what these binary variables are going to encode. Also, of course, we have to decide exactly one price for every soda product, and that's what this set codes. But also, Pete mentioned that what we also want to include is some business rules. So one of these business rules is that we have, in this case, two family of sodas. One is clear and the other is dark, and we want to limit the number of discounts that we're going to offer for every family. In this case, it's going to be only two, as I'm going to show. And this is what this line is encoding. What it's saying is, if we sum all the prices that are not the normal price, that's what P0 is, and for products that belong to this family, either clear or dark, we'll see later on, that number of discount prices is going to be a maximum number for every family. And to link the decisions with kind of meaningful quantities, we say that sales is going to be the product between the forecast sales for every product and a given price times the decision. And the revenue is going to include also the price, of course, in that product. And the investment, what we are going to define as investment is essentially the money that we will have kind of put on the table by keeping the same price. So how are we encoding that? Essentially, we take the estimation for the new price of demand minus the original estimation of demand for the normal price. And that quantity we multiply by the original price times the decision of taking a given price or not. And bear in mind, we're putting here a plus sign. So in a reasonable world, always the prediction of sales for a lower price should be bigger than the prediction of sales for the regular price. But we will see that since we're just doing estimation, it's not the case for the estimates that we are building. And also we want to put a cap on investment, a given quantity. So that's the logic, that's the business model. It's not a complicated one, but interesting enough to see how we can model all these choices. First, we need to define the data that we're going to use to feed this problem. What are going to be the variables? So we said that we have both product and cost per unit, and that is in the table that we had. So essentially, we are going to use these forecast sales. We're going to keep the index, this product of both product and price, and we are interested in looking at the predicted sales that we're going to get. So we get the sales. Essentially, this is going to encode how much sales we're going to get for every combination of product and price. And that's what that little code is doing. We're also going to define the soda families. So here we are essentially mixing every product with a family, either clear or dark. And so the set of families is just the image of that dictionary. And the set of soda products is the index of this dictionary before, and that's what these two lines are encoding. And we're going to set to the maximum promotions for every family, and we are going to define the maximum investment to this quantity 750. Now we are essentially ready. We have the index set of products and prices that we want to consider. We have also here the predicted sales for each one of those, and we have the sets and the constraints and the investment. Also, we have to define the normal prices. As you remember, one of the constraints was to limit the number of promotion prices for every family to 2 in this case. So essentially, we go over the list of product and prices, and for every product, we set the normal price as the maximum price in the list. That's what those lines are encoding. And as I said before, since we are doing machine learning, this is not a guarantee tool that will always give what we expect to have. And one of those things that doesn't really comply with the logic is that getting lower prices doesn't always mean that we are getting predicted higher sales. And you can verify that with this little bit of code. Essentially, we are counting for the prices that are not the normal prices if the forecast sales is above the sales of the normal prices. And as we see, only in 20 of the 27 possibilities, we are getting boost sales. We have to remember all those little details. So, okay, we have the data, we have the model, the math model, and now we have to build the actual Python model to do the calculations. Let me start by defining the variables. This is going to be fairly simple. That's one of the nice things of Python and also on the new Gurobi interface for Python. So, of course, we bring in the Gurobi Py library. We define a new model. In this case, it's going to be just an empty model. And now the select price, essentially the X variables up here, is just this line. We are going to add a set of variables. That's what this is saying. Indexed by this case pairs of indices, both product name and price. We're defining them to be binary, and they are going to be called X something. The sale is going to be a positive variable, and by default, all continuous variables, all variables are continuous and positive constraint. So that line is essentially that line. The same for revenue, and for investment, we're going to encode in this line both the zero lower bound and the upper bound. By defining upper bound is going to be max investment. So there we go. We have the variables defined, and what we need to do now is to glue them together with the constraints to really reflect what we have in the model. So let's do that. So we have three basic relations that link sales, revenue, and investment with the binary decisions. And the code for the first one is essentially taking sales equal to the set of variables, the select price variables, product with the forecast sales. So this will be essentially the inner product between those two vectors of variables and constants. And this is saying that the constraint is going to be sales. It's just one constraint. Now, the next one is a bit more complicated because it's not just adding a product, you also have to bring in the actual price to get the revenue. So to do that, what we do is says revenue is equal to the sum, the quick sum of the sales for every solar product and price times the select price, which is the binary variable, and we do that for every BP in the product price. Essentially, we are encoding that big sum here over all B and P in this larger expression. And for investment, well, it gets a bit more tricky, but still it's not too bad. Essentially, first we are encoding this positive part to the maximum between 0 and this difference between the forecast sales and the forecast sales to the normal price. And the remaining of that, or the result of that maximum, is going to be multiplied by the normal price and the select price, the variable. And we are summing over all BP in the product prices set. And that's encoding the investment constraint, linking the binaries with investment. So that's not too bad. What about the other ones? The ones linking the conditions on the binaries. As you can see, the first one, actually, you have to notice, here we have the sum for every soda product, that the sum should be equal to 1. And Gurobi added a simple way to handle these situations, which is the add constraints. This is a multiple constraint set. So we are selecting all the variables for a given soda product here, and we are summing over all the prices. That's what this little thing is encoding. So essentially, you're selecting a slice of the set of variables. And that sum should be 1 for every soda product that we have. And the name is going to be one price, and it's going to encode also the soda for each one. So this is really encoding this whole line, which is very nice. And also, for the second one, it's a bit more complicated, but not too much. So it's also a set of constraints, because for every family, we're going to add up a constraint. And what are we going to sum? So we are summing over all the soda price products, but only if the soda family for the product is the given family that we're working on, and also if the price is not the normal price for the given soda product. And that should be less than or equal to the given maximum promotion for the given family. So this is very handy. Actually, it's abusing the list comprehension from Python to really select which indices you want to bring into a given constraint. So this is encoding this whole logic, and I find it very neat. So, okay, we're almost done. We only need to set the objective. We set the objective with this line. We are going to maximize, in this case, sales, and then we call optimize. And then Gurobi works. This is not really a hard problem. It takes no time. And as you can see, we get an optimal solution in almost no time. Let's inspect the solution. An important thing to always check is whether we have an optimal solution. In this case, we do. So we know that we have a feasible and optimal solution for the problem. But it's not really enough just to check a number or an optimality status. We probably also want to see what the solution looks like. Of course, we can look at the sales, the revenue, and investment, and the investment is indeed under 750, which is what we wanted to, and the sales is that number, and the revenue is that other number. But what about the decisions? Which things went into a promotion and which ones did not? So to do that, we built a little table. What we're doing essentially, for every product, we are going to store the price, we're going to encode this, if this is a discount or not, and which family this thing belongs. So we are going to look for on all the soda and price products. And for those variables that are essentially one, that's the if that we have, we are going to add the product. We're going to add the given price associated with this. And to detect whether this is a discount or not, we compare the price with the normal price. And if it is below the normal price, then it's a discount. And then we also put the family for which this product actually belongs. And then we set the index to the product, and we sort according to family, and we print this beautiful table. Essentially, we get the price for every product, and we are seeing which one are discounts or not. And you can see the clear families here at the top, and we have only 2 discounts. And also for the dark family, we only have 2 discounts, which is what we expected to have. So, okay, this is showing that the logic is sound, but probably we should do another experiment. So we have a correct solution to the given nominal data that we have. But in reality, remember, I mean, we took those decisions looking at one prediction. And actually, we could build many more predictions. So what we could do, and what most people do actually when doing this kind of experiments, is really what-if analysis. And I'm going to do not just a few of them, I'm going to do 100 what-if scenarios analysis. And remember, the forecast is coming from these random forest regressors. And these random forest regressors are really stochastic in nature. And if you change, in this case, just the seed, you are going to get a different estimation, a different prediction. So by doing this, by setting the seed and then calling the random forest regressor, I am generating 100 different possible estimations of demand or forecasts of demands. And what I'm going to do is not to optimize with this new data. I'm going to evaluate the solution that we had before for this only problem, how it behaves in these other possible estimators of the sales. And what I'm going to do, I'm going to essentially store the sales, the revenue, and the investment for each one of those possible predictions, okay? And to see something, I'm going to build these graphs. So these graphs is just a distribution plot on how sales behave, and not only sales, also the 3 key performance indicators. So as you can see, sales is not just one number, it's really kind of a broad distribution here, and actually center in the number that we had before from the deterministic problem, as you may. But more interesting probably is that if you look to investment, so investment, remember the condition that we had was 750. But remember, we are now evaluating the given decision on different predictions for sales. So now about 50% of the time, actually it's 51 out of the 100, we go over that 750 limit. That's something to keep in mind. And if you look even to revenue, I find interesting. So what you get is not really a symmetric distribution. It's more skew to the lower end. Something interesting here. What I'm showing this is not to say, oh, well, okay, we did some prediction, one prediction, actually, we did an optimization, and then if we evaluate over a wider set of predictions, we get kind of a moving target. Can we do something about it? And my whole point is that you can. Certainly, you should always kind of evaluate how your given solution behave on different possible future scenarios, and this is just one way to do it. But more than that, I just want to remind you guys, nowadays, you can also take decisions taking into account multiple possible scenarios, and that's something called stochastic optimization, which has come a long way. So that's it from my part.
Okay, so real quickly here, I'm just going to go through some deployment issues. Should be looking at my screen, showing you the Opalytics cloud platform. So this is a web-based deployment platform. Talking about the machine learning section. So with machine learning, there's a bit of an open debate as to the extent to which you should be writing custom code at all for machine learning. And that's because, as you might have guessed, the workflow for a lot of these supervised learning tasks where you assess and then train and then predict, the workflow is very similar even for very different tables and very different types of data. The question is whether you should be coding it up, to what extent you should be coding it, or whether you should be using some sort of off-the-shelf tool. So just to give you a brief demo of what I mean, you can load up a historical table here, and it just accepts all the columns and all the rows. And then on the optimization, on the engine parameter form, when you've loaded up a historical table, you can orient a tool to the table, because you just need to specify what the dependent column is, and then if other columns are to be ignored, you can leave them out. And there's another table I can show you that specifies which columns are the categoricals, although by default, it will just recognize all string columns as being categorical. So that enables you to do, with really little to no code at all, enables you to populate these basic tables for these common forms of machine learning. So if you want to test bagging with a given number of estimators, you just put a row in this table. And if these four types of machine learning algorithms are not enough for you, there's a custom section, and this is demonstrating the power of Python, where you can just drop in a simple Python function here. This is a function I wrote myself that's doing linear regression by doing it programmatically. So you could pull anything from sklearn in here, and this would be a good slot to do some of the more advanced hyperparametric optimization stuff. And then if you run it in experiment mode, there's two modes. I went through that pretty quickly, but there's two modes. If you run in experiment mode, you just get the same sort of result for, this is the R2 score, and you can see that the big random forest is the best, same as before. This is all the same data as before. And then there were two modes. So once you've experimented and found what you like, you can populate a fit table, whichever fit entry you like best. Here I populated big random forest. And when I solved it in fit mode, what fit mode does is it creates that predictor object that I showed you before in the notebooks. Here it's presented visually, and if you publish it, then you can essentially create an engine capable of prediction, and it just adds it to the set of engines that are available. So the engines or the apps are over here. You can see the published predictors. That's the exact same little graphic reminding you what it was, and it knows what it's supposed to do. It knows its schema, right? So this is a key concept. When you're trying to do sophisticated work, when you're trying to plug components together, it's good for each component to be robust and to know what sort of data it's supposed to expect and what sort of data it's capable of producing. So that's a key theme. So these predictor objects, they remember what their schemas are like, what the table is like, what the dependent and independent columns are. Now for the optimization piece, I think I teased this before. So this is a script that was loaded up into the platform. And this script, it's also is available online. This script uses the TICTAT library. So this is available on PyPy under an open source license. It's not included in this Anaconda, but it's a simple, pip install task to install it. And you don't need to use the Opalytics cloud platform to run it on standalone data. So the key thing that TICTAT does is it helps you define the input and the output schemas. and you can actually define some data rules too. So the data rules are, in my opinion, they're very handy because you never know when somebody's going to pass you bad data, and you want to have good error messages when the data is failing sanity checks. But telling it the input schema, the output schema, you enable file I/O. So there's a command line section all the way at the bottom. Before I scroll down there, notice again the forecast sales table. This is all focused on just optimization, right? So all those ancillary independent columns have been removed, and we just have product, cost, and expected sales. This solve section, I'm not going to walk you through it, but you can study it for yourself and verify that it's very similar to the code that Daniel just showed you. So as promised, you can, you put together a scratch solve and you can copy it over piece by piece and build a standalone solve. This is a standard Python trick where this file can now be run from a command line, and take that, will parse your command line arguments, figure out, deduce what file types you're trying to read and write from based on the file extensions, so you can run this in a standalone way. But when it's loaded up into the platform, then it knows its schema. And because it knows its schema, you can do advanced things like connect two engines together. So here I'm not going to do it. I did it already, but I'll show you what I did. I'm connecting that predictor object that I showed you initially with the optimization engine object. That's the Python script. When I did that, that connection was made by only performing 3 steps. So I had to select the predictor and the optimization engine, select the column that has the independent column. And once I know the table in the column that has the independent column, then the tool is smart enough to organize the schema for you. And so this engine that was created has this schema over here. As you can see, it takes as its input table for forecast sales, a table that doesn't have a prediction of sales at all. It just has all the independent columns. And then when you launch this solver, it'll first formulate this table, create the dependent column, and then knows how to populate the dependent column into the table that the Gurobi optimizer needs. And to quickly go all the way back up here. Here, Predictive, Optimize, and here's this engine. As promised, it has that special table, right? It has independent columns, but doesn't have the predicted sales. And when you launch solve with this, it does the prediction, and then it does the optimization, and it gives you a nice set of reports. So you can see the KPIs, and you can see what prices were made. It's easy to sort and see that, okay, here are my discounts, and here are my normal prices. Okay, that covers that range of material.
We are ready to go to the questions.
Excellent. Thank you very much, Peter and Danielle, for a great presentation. We have a couple questions from someone in the audience who's asking about the visualizations you presented for the machine learning algorithms. So what is the interpretation of these visualizations, and how would I decide which algorithm to choose based on the results of these visualizations?
Yeah, the visualizations are just there to drive more intuition. Personally, I take more value from calling things like cross-val score in bulk, but the visualizations give you a feel for what the error spread is like. So it might help you be more aware of an estimator that has a high degree of accuracy, but when it fails spectacularly. So that's a sort of, like with any distribution, you can assess the distribution's mean and standard deviation, but it's also nice to visualize it.
Great, thank you. The next question is somebody who's wondering, Danielle, you mentioned stochastic programming. Does Gurobi interface well with any specialized stochastic programming tools?
Actually, most stochastic programming tools that I know in the end just translate into a regular MIP or even an LP. Actually, you don't have always to go to MIP to really do stochastic optimization. And actually, many people do use the just LP side as a stochastic programming. So essentially, the interface is just build a larger model. That's what's going to happen, really. Thanks.
The next question is from a user asking, what is the advantage of using machine learning over standard linear multiplicative time series forecast models?
So, yeah, I'm not sure I completely understand the question. So my familiarity with time series, it's an additional, it's a separate piece of machine learning that's focusing on timestamp information, on time series-based information. It doesn't do the same work of sort of broad-scale inferences. So I don't think you can do, that time series just looking at that one column that tracks time and making predictions based on that. Whereas what we showed is that we're capturing, a broad range of data that influences the dependent column. So they're not really, they're sort of orthogonal to each other. They don't really compete for the same, as choices for the same type of tasks. That's my understanding of it.
Okay. Danielle, this one's for you. Regarding the last part in which you run the optimization multiple times with different seeds, how is it possible that the investment limit constraints are being violated while still getting values for the decision variables?
Good question, because it means that I didn't explain well enough. So no, we are not rerunning the optimization. If we had, then we will have never violated the constraint. You're right. What we did is, given the decision that we took using just one sample, we evaluated that decision under different predictions. That's what we did. And that's why we see that for some of those predictions, we are over the stated limit. That's the explanation. Thank you for the question.
The reason I think there was such a high number of infeasibilities is because the constraint that was applied, the investment constraint, ended up being an important constraint, so it was tight. So because, or very nearly tight, right? When it was a max of 750, Gurobi came up with a solution that was 748. So of course, any little variability can put it over the edge, right? And the thing to bear in mind for this business problem is that investment constraint is not really like a hard constraint. It's not like when that constraint is violated, the business breaks down. It's more like the investment constraint is to give some guidance as to the extent to which they're trying to invest in the sales operation. What would happen at that next step is that you would do the simulation and you would say, okay, the constraint is tight as expected. It's violated around half the time. That's actually not that surprising. But we can dive into sort of the extent to which it's violated. Like when it's violating, is it just going a little bit over budget or is it going a lot over budget? And if the simulation indicates that it's going over in an unacceptable way, not just with an unacceptable frequency, but it's going over, it's far exceeding it too high a percentage of the time, you could always just re-optimize you could always just go back to the first step and use a tighter version of the constraint. You could always just say, okay, I'm not going to use 750, I'm going to buffer it. I'm going to give myself a buffer and redo this whole thing with a constraint of 700. Being a little closer to the business problem, that's kind of the way the logic would work there.
Great. The next one is, how do we know the optimum is global and not local?
So, well, Gurobi will solve an MIP using branch and bound, and essentially it's a proof that you are getting, if you solve optimality, the optimal solution, and if you stop early on, you are getting a proven quality of the solution, assuming that nothing numeric goes wrong, which sometimes may happen, but doesn't happen very often.
The next question is, I assume they're asking about using machine learning. Does Gurobi provide machine learning algorithms? Because they're asking, can we run a classification model for our historical data using Gurobi?
Gurobi doesn't offer a machine learning suite or tools directly implemented in Gurobi, but many of the machine learning techniques rely at some point to win optimization, and you can use Gurobi to solve those problems. And actually, many people is working on actually using alternative algorithms to achieve what you really want, which is to get good predictions. But that's still part of research, and you are welcome to try, of course.
I think this is probably the last question we have time for. Is it possible to integrate the predictive function into the Gurobi formulation, even if the predictive function is nonlinear?
So that's an excellent question. We get that fairly often. And the short answer is no. I mean, not upfront. Gurobi cannot handle kind of custom functions and how the data is behaving, but you can model it as a different optimization problem. And that's what I was pointing out before on this stochastic optimization view of the problem. As I said, I mean, there are a couple of books where you can look at how to do that and actually discussing what's the correct way to model it. It's very user dependent, and there is a long discussion about it. Short answer, you can, by using a different model, but you cannot give right away as an input to Gurobi a custom function for the data.
Great, thanks, Daniel.